Hi, everyone. Thanks for having me. My name is Eray. I'm a senior data scientist at the Google Econometrics team under Ching, who was just at the panel. And today I'm going to talk about how and why we should use counterfactual models in our business decision making. It's a pleasure to be here. It's a great pleasure to share this stage with everyone today, and thanks to the organizers. All right, this is a non-technical talk aimed at a seasoned practitioner, and I want to start with the big picture question of why do we need counterfactual reasoning and why do we need causal models in our business. So frequently in business, we need to make decisions between different kinds of interventions. We need to decide who should we target with our ads. We need to decide should we run a marketing campaign or not. We need to decide who should our salespeople talk to and who should they prioritize and who should they deprioritize. And when thinking about these kinds of questions, I want to frame our model of the world and our thinking using these two questions. The first one is, what do we need to learn? And the second one is, can we actually learn it from the data at hand? So diving deep into the first one, what do we need to learn? Is this a predictive task, and can we make do with learning from historical associations? Or do we need to make statements about unobserved counterfactuals and decide between interventions? And once we've decided that we want to learn something, and hopefully that is a counterfactual because that's usually what's the relevant thing in business decision making, the second step is deciding whether we can actually learn it from our data. Do we have any useful information or variation in our data set that would help us learn that? And what do we need to believe about our data and our data generating process for our answer to be actually the causal answer that we seek? And the main takeaway that I want to leave you today with is that causality is not a property of the model or the algorithm we use, but it is a result of our assumptions on the data generating process and our beliefs on the world. All right, so I'm going to jump into an example. I'm going to run through two examples, and because the organizers asked me to talk a bit about marketing and sales, the first one is a marketing example. So let's take a hypothetical situation where we need to evaluate the impact of our marketing campaign. Now, for simplicity, let's suppose we have no control over how the campaign was run. We are just tasked with this problem of evaluating its impact and deciding whether it was worth it or not, and figuring out a way to quantify its returns. Now, what do we need to learn to answer this question well? What does it mean to measure the impact of a marketing campaign? Well, I don't have to try to convince you really hard that this is a counterfactual question, and we need to know the counterfactual of what would have happened without the marketing campaign. And this is a question about an unobserved world. We live in the world with the marketing campaign, but we want to make inferences about the world without it. And it is very tempting to jump into machine learning in a situation like this. We collect a lot of data about our business. We probably know who interacted with our ads, who converted as a result of seeing our ads. We know how much our customers are spending. We have high resolution data. And we can train a machine learning model to predict revenue under marketing and revenue without marketing using different sources of variation. We can either teach it from the cross-sectional variation of the data, training it between cities with marketing versus cities without marketing, or we can leverage the time series variation. We can teach it using periods with marketing versus periods without marketing. Now, suppose we dived into a situation like this. We have a marketing campaign run on a city, and we see that the cities with the marketing campaign have X% higher revenue. As a result of our machine learning model, we produced the outputs under marketing and produced the outputs and predictions without marketing, and there is a difference. And the predictive ML model can help us make statements like, the cities that had marketing campaigns had X% higher revenue. And this might be a correct statement, but it's not really informative for the decisions we're trying to make. And it's not really teaching us about the counterfactual. Now, there are many reasons why this scenario can go wrong, But if you bear with me a second, like a model trained on the cross-section can be picking up a bunch of other factors, and I'm sure you can come up with many other explanations here. But one of the potential reasons how this can go wrong is, how do we choose where to run the campaign? And are we picking up the effects of us choosing a city with an established organic growing user base versus the actual effects of our marketing driving growth? Can we distinguish these two things from the data at hand? Now, this is where counterfactual modeling comes into play, and this is where causal models are useful. Well, we need to learn what would have happened without the campaign. How do we do that? We can construct a causal model or a counterfactual model. And there are many, many things in our toolkit to do this. We just talked about synthetic controls, difference in differences, modern approaches to difference in differences with Callaway-Santana, other panel models. We can construct a counterfactual prediction using any one of these things in our toolkit, and hopefully that is going to get us a causal answer. Or if you're lucky enough to run a randomized control trial, you can also pick a random subset of cities to run your marketing campaign and randomly pick another subset for the holdout and try to learn the counterfactual from those who didn't get to campaign. Jumping into another example here, this is about sales and touches a little bit of what my colleague Maher talked about this morning. So suppose we want to understand the impact of a sales pitch. What is the impact of our salespeople pitching our product to our customers? Again, this is a counterfactual question. To answer this well, we need to understand what would have happened if we didn't do any sales interventions. And it is a very rich, data-rich domain, and we potentially observe how our salespeople interact with our clients, how many phone calls they made, how many of those got answered, how much our customers are spending, what was their spending trajectory. And again, we can use our rich data set to build a sophisticated ML model. We can throw a neural net at this if we want and try to predict what would have happened with the sales intervention and compare that to the prediction without the sales intervention. But again, going back to the question at the beginning, what is such a predictive model learning from? It is learning historical associations between sales and revenue and learning from the differences between clients that receive sales pitches and clients that didn't receive sales pitches. So do we have any useful information or data to help us answer the actual causal question of what would have happened without the sales intervention? Can we use anything, any source of variation in the data to help us distinguish between organically growing customers being pitched to versus salespeople actually driving growth themselves? Now, to answer these things and try to get around them, we can again go to causal inference modeling and model counterfactuals using some kind of propensity model to account for selection into receiving a pitch based on observable characteristics of the advertisers. So again, we have a lot of tools in our toolkit for addressing situations like this. We can use something like double ML or some version of inverse propensity weighting, where we model selection into receiving a sales pitch as a function of observable characteristics of a client and try to underweight advertisers that tend to have characteristics of receiving high sales pitches and overweight advertisers that have the opposite. Again, this will get us a causal answer through double ML, and we can try to use that in our decision making. Or if we're lucky enough to run an RCT, we can actually run an experiment where we pitch to a random subset of our clients and hold out another random subset, and again try to learn the counterfactual of what would have happened without the sales pitch from those in the holdout group. Now, by now, hopefully, you are actually convinced that, like in a lot of business scenarios, what we need to learn is not associations, but counterfactuals to make decisions. And we have a lot in our toolkit as seasoned practitioners to build those counterfactuals through some kind of a modeling approach. We can do synthetic controls, double ML, RDDs, instrumental variables. We can run experiments. And I want to argue that this is not where our job as practitioners is not is done. The real part of the job begins after we hit run on the model or run an experiment. And applying a causal inference algorithm or a model does not guarantee that we will get a causal answer, nor does an experiment guarantee that our answer is the actual causal answer we're looking for. Now, going back to some of our examples we talked about, I briefly talked over this where we said we can run a synthetic control model to construct a counterfactual of what would have happened without the marketing campaign. Now, again, the job is not done when we run the synthetic control model and report the point estimates and the standard errors. We need to ask the question of what do we need to believe about the data for the answer we provide to be the causal answer we were seeking. There are many reasons why a synthetic control model can go wrong, and I'm sure you can come up with many scenarios, but here, let's suppose we were treating a particularly big city like New York City, and our other control cities were relatively small cities, and we were trying to construct a counterfactual, but can we really construct a credible counterfactual based on all those other smaller cities to capture what New York's sales numbers would look like? Now, you might be thinking, surely if we run an experiment, we're probably good. Suppose we ran a marketing RCT and we took 10 different cities, randomly put 5 of them into the treated group and 5 of them into the control group, and we ran our marketing campaign in the treated ones, and we're learning the counterfactual from the control ones. This is an RCT. It's the gold standard in causal inference. Is our job done now? And I think you will agree that no, our job is not done, and the world is not stable, and there are many things outside of our control. And even with an RCT, you need to make assumptions about the data generating process, and there are things you need to believe about the world for your answer from the RCT to be the causal answer you are seeking. Again, in this example, suppose we were running our marketing RCT and our competitor was also running a campaign in some of our control cities. You can see how things can go wrong even with an RCT, and there are many, many examples where this kind of things happens and we don't recognize it because we don't dig into our data and we don't talk to our stakeholders. Going back to the sales effectiveness example, suppose we ran a double ML model using advertiser characteristics to model our propensities and get an answer. Again, we're not done there, and we need to ask, what do we need to believe? Do we have overlap in the data? Can we construct credible counterfactuals from advertisers that were not pitched to understand what would have happened to those that were pitched? And are they comparable to each other? Do they share any characteristics? And probably there are factors we don't observe about who our salespeople talk to and how they decide to spend their time, and we cannot capture everything in our propensity modeling, and this is where things can go wrong, and this is where we need to, again, keep talking to our stakeholders, our domain experts, to evaluate our assumptions and what we need to believe about our models. Again, you might be thinking, we can just run an experiment, and maybe we are lucky enough to run an experiment, and we've convinced our leadership that it's worth the cost. We are holding out a subset of our clients that we're not pitching to them, and we're pitching to a random subset of our clients. And we can get an answer from an RCT, but again, our job is not done, and there are many ways how an RCT like this can go wrong. What if our customers are talking to each other? And what if some of our customers in the treated group are talking to their friends in the control group? Again, an RCT does not guarantee that we get a causal answer, and we have assumptions we need to make about the world and evaluate them in order to ensure our stakeholders, our decision makers, that they can trust the numbers we provide them. The message I want to leave you with today is that causality is not a property of the data or the model or the algorithm we pick. It is a result of our beliefs and assumptions on the world. And no algorithm or method can guarantee that the answer we get are causal answers. That is a function of our beliefs and assumptions on the world. And when we're using these abundance of causal tools and techniques as practitioners, I want to reiterate that the real job begins after we click run on our causal inference algorithm and get the answers. And we should not stop by just reporting the point estimate and some version of a p-value or a standard error or a Bayesian credible interval. We need to assess the credibility of what we need to believe to get a causal answer, and that is where the real job begins. And that is all I have for you today. I'll be happy to take any questions if you have any.
So a question did come through. Is causality in an RCT more likely to be guaranteed with a large sample size because of the central limit theorem?
I don't think I can connect it to the central limit theorem, but under certain scenarios, it is easier to believe the assumptions you need to believe for an RCT to go through. You could be in a world where you don't need to worry about spillovers between subjects, and with a large sample size, you might have credible intervals or confidence intervals that are tight enough, and you can run sensitivity analyses to violations of some of your assumptions, and you can say, even in a worst case scenario where my assumptions are violated to a certain extent, our answer will still go through. And this is the kind of thing that I love to do. Rosenbaum style sensitivity analyses, I think, is a very useful tool. And I think sometimes it's easier to achieve that with RCTs for sure. Yeah.
Brilliant. Thank you. That was all the questions that you sorted. Got off lightly.
Thank you.
Thank you.